I'm a postdoctoral fellow on the BIOSPEC project funded by the EUR Manutech-SLEIGHT. And I will talk to you today about experimental decorrelation requirements for the spectral unmixing of fluophores using multiple wavelength excitation fluorescence spectroscopy. But first, what's the BIOSPEC project? Briefly, we're working on two distinct clinical applications, but with the same aim, which is doing quantitative analysis of biomarkers using spectroscopy. Here, you have an example in dermatology, and especially of old people who is elderly and had a bald crane, and he has actinic keratosis, which can be enhanced and then treated using a photosynthesizer called protoporphyrin 9 or PP9 here. And this photosynthesizer has the great ability to become fluorescent and then emit a reddish signal under blue excitation. And the aim of the BIOSPEC project in this thematic is to do a spectral analysis using hyperspectral imaging and optical modeling to be able to correctly to increase the sensitivity and also better delineate the CREATIS actinosis during the treatment. And on another clinical application, we're also working in neurosurgery, where the neurosurgeon during the neurosurgery, the neurosurgeon wants to remove a glioma, which is a diffusive brain cancerous tumor, and to be able to enhance the glioma, the tumor region in the whole cortex, he is using also the protoporphyrin 9, which then still emits here in a reddish color. And thus, we have previously developed an experimental setup that you're able to see here, which enabled to acquire a fluorescent spectrum. But the question is how to do a successful, efficient spectral unmixing of the measurement we have to be able to correctly quantify the protoporphyrin 9. So, in fluorescent spectroscopy of the protoporphyrin 9, there are two main approaches. The first one, which is a quantitative approach, estimates the PP9 concentration in absolute units, but it requires optical modeling, and a part of the scientific community is working on this aspect. And on the other hand, there is a more semi-quantitative approach, which better studies the spectral shape of the fluorescent measurement we acquire, but it requires a lot of knowledge on the fluorescent biomarkers that are present inside the measurements. Indeed, in both approaches, we are studying two different shapes of protoporphyrin 9 here, so two distinct chemical forms. Each of these forms is emitting with a distinct maximum of emission. And considering these two fluorescent spectrum, it enables to correctly quantify to correctly classify the biological tissue that is measured. But in biological tissues, there is a lot of other fluorescent molecules that are called endogenous fluorophores, and we need to consider them because they are present inside our measurements, and if we do not consider them correctly, or if we badly modeling them, then there is an impact on the estimation. On the estimation of the protoporphyrin, which is an element of the porphyrin families. And especially if we look at the literature, here you have two distinct graphs. Each graph is plotting a lot of distinct spectra, fluorescent spectra. But if you look at on the left side here, you have first article from the literature where the lipofuscin, which is an endogenous fluorophore, is modeled here by the green spectral shape. And the same fluorophore in the article from the related to the right graph is plotted here in the yellow, according to the yellow curve. But if you consider the spectral shape of the right article or the left one, you will have an impact on the quantification of the two forms of the protoporphyrin 9 we are looking at. And this can lead to an overestimation or an underestimation of the correct quantity of PP9, and especially it could lead to an high overestimation of the PP9 concentration if we consider the case related to the article of the right side of the previous slide. And this can lead to an overestimation or a bad classification of the tissue. In other words, here on the vertical axis of the both graphs, you have the relative concentration of one form of PP9, and on the left axis, you have the relative concentration of the other form of the PP9. And if you overestimate it, and here, the right part is an inset of the bottom of the main graph. And if you overestimate the concentration of each form of PP9, then you move the tissue that should be classified as healthy to tumoral ones. And thus, on both aspects, you will lead to extra removal of the patient lesion, and then it could lead in neurosurgery to bad classification and then removal of the whole cortex. So to try to avoid this crosstalk effect, we suggested to use we developed a new method to extract correctly the concentration of PP9 from the measurements, which include all the other fluorophores also. Briefly, compared to state-of-the-art, who's doing a lot of a priori on the spectral shape of the fluorophores that are naturally present inside the biological tissue and thus inside the measurements, we suggested to use an other excitation wavelength of the fluorescence, and then we move the a priori, which is originally on the baseline, to the quantum yield of each form of the fluorophore we are looking at, so each form of the protoporphyrin 9. And and thus we are able to estimate the spectral shape of all the other fluorophores that are naturally present inside our measurements. But we only assume that the spectral shape of the fluorophores of the endogenous fluorophores remain constant between the two excitation wavelengths. And we demonstrated on simulated glioma that it works pretty well, and especially in case, so here you have a simulated glioma. Each color corresponds to a distinct pathological category of the tissue. And we notice that in cases where the state-of-the-art methods here in the middle of the graph are working pretty well, so are able to correctly recover the categories from the ground truth simulated glioma, our method in the bottom of the graph is worked also pretty well, but also in cases where state-of-the-art method fails, our method is able to recover a high sensitivity, so a correct delineation of the boundary between tumoral tissues in the middle of each image, and also the distinction with the healthy tissue on green around the tumor. But if we go to experimental aspects, what does that mean? And especially in reality, in real measurements, how to be sure that the second excitation wavelengths add a lot of information to be able to correctly estimate the baseline, so the spectrum of all the fluorophores that are naturally present inside the tissue, and which limits the current efficiency of fluorescence spectroscopy method right now. So thus, we compared two different experimental systems. The first one, which I will call system A, which excites the fluorescence with LEDs. Each LED have a quite wide excitation spectrum. And on the right side here, you have a system B with laser diode, who have a thinner spectral emission. And then we want to compare the impact of these two distinct fluorescent excitation sources on the decorrelation between the measurements, because high decorrelation will lead to a better an addition of information with two excitation wavelengths of the fluorescence compared to a single one. Briefly, we will look at distinct region of the spectrum that we acquired, and we'll look at the correlation coefficient between the two measurements in first a region where there is only noise, a second region which is only related to endogenous fluorophores, and here finally the region of interest which contains the information related to protoporphyrin 9. And we will compare the correlation coefficient between the two measurements with the ones of the simulated phantom we used for the previous results. And briefly, so mainly if we look at the region here related to endogenous fluophores, we need to have a high correlation coefficient, which in order to be sure that the assumption that the spectral shape of the endogenous fluorophore remains the same between the two excitation measurements. Thus, we did it. Here we compared the yellow bars related to the numerical phantom we used for simulated glioma with the measurements done with the system B, so with laser diode excitation of the fluorescence, and then with the blue bars, which correspond to the measurements acquired with the LED excitation for the fluorescence. And we are looking especially at the boundary between the healthy tissues here and the low-grade glioma or low-density margins of the. So we are mainly comparing the first group of bars with the group number 2 and 3. And we notice that in the region where which is related to endogenous fluorophores, the correlation coefficient remains quite high for both the numerical phantom and the system and the measurements done with system B compared to the one of system A. And in addition of that, we are also able to see here on the graph of the right side that the correlation coefficient related to protoporphyrin 9 becomes really tends to 0, or at least to a lower value for the phantom and the system B compared to the system A. What does that mean physically? It means that here using two excitation wavelengths with a system B, so with laser diode excitation, would able to add a lot of more information to the measurements compared to the one with LED excitation of the fluorescence. Thus, the estimated baseline method would, we hope that the estimated baseline method would better work with system B, with measurement done with system B than with system A. So briefly, we previously demonstrated that using multispectral excitation helps to improve the classification of tissue and synthetic data. And moreover, we quite now demonstrated that the correlation coefficient could be a criterion to better to select the best processing method in a sense that we are able to better determine if there is a real add of information using two excitation wavelengths of the fluorescence compared to a single one. And as a brief outlook, we want to apply the post-processing method on a lot of clinical data we are currently acquiring on the neurosurgery operating room. And we also hope that correcting the absorption and scattering would better also enhance the correlation, especially in the PP9 region. So finally, I want to thank you for your attention and acknowledge a lot again for the Manutech-SLEIGHT for funding this project. If you have any question, I would be pleased to answer them.